Think of nothing. What do you see? Perhaps a blank screen, a black void, a vast emptiness. You might imagine a vacuum, a place drained of matter, of light, of radiation, a space so utterly barren that it defies form and substance. But go further. Strip away not only particles and photons, but the space itself. Remove time, remove direction, distance, and dimension. Now ask again, what remains? This is not the emptiness of outer space. This is true nothingness, a concept that lies far beyond our senses. It is not silent, it is absent. No space to be silent in, no time to pass in. It is the absence of all things, including the stage upon which things may exist. This idea is hard to grasp because in our everyday lives, we are never without something. Even in the deepest vacuum of space, there are still quantum fields, invisible energies, and the gentle ticking of time. But imagine a reality with none of that. No before, no after, no here, no there. Just nothing. This is where the questions begin. If the universe had a beginning, what came before? If time began, how can we speak of before? Such questions lead us to the very edges of science, philosophy, and imagination. And somewhere, hidden in that paradox, may lie the secret of our origin. The story of everything may begin with nothing. For thousands of years, humanity has gazed at the night sky and asked the oldest question of all. Where did it all come from? The stars, the earth, time, space, existence itself. What was their origin? In the book of Genesis, the opening line is simple yet profound. In the beginning, God created the heavens and the earth. But what does that beginning truly mean? What came before it? What existed before creation itself? The text does not say. It offers no glimpse into the moment before the moment, into the canvas upon which existence was first painted. And perhaps that silence is deliberate, because perhaps there was no before at all. Religious traditions have long attempted to frame the mystery of creation within the language of divine will. In Christianity, God is eternal, existing outside of time and space. The universe was not born within a timeline, it is the timeline. Time itself is a part of the creation. This idea is echoed in many faiths. In Hindu cosmology, the universe undergoes endless cycles of birth and rebirth, driven by cosmic rhythms that stretch far beyond human comprehension. In some indigenous traditions, the world is sung, spoken, or dreamed into existence. And in each of these views, the origin of all things is not random, but purposeful. Yet these stories, as rich and meaningful as they are, often leave the philosopher and the scientist with more questions. If God exists beyond time, what does that mean? If time began with the universe, can anything truly exist before it? Can causality exist outside of time? These are not merely theological riddles. They strike at the very structure of logic and reason. Even for the secular mind, the question remains, if the universe had a beginning, why did it begin? Why was there not simply nothing? The mystery is not just religious, it is existential, and it is universal. Modern cosmology, built not on scripture, but on mathematics and observation, echoes the ancient whisper of a beginning. The expansion of the universe, the cooling of radiation, the distant afterglow of the Big Bang, all suggest that our cosmos had a starting point roughly 14 billion years ago. It was not eternal. It was born. But even with these powerful tools, science too runs into a wall. The moment of creation lies behind a veil, a boundary where space and time cease to behave like anything we understand. The question then returns, what came before? Or perhaps more accurately, can we even speak of before when time itself was born? And so, religion and science, though often seen as rivals, converge on the same frontier, a place where answers dissolve into silence. Whether you believe that a god spoke the universe into being, or that it emerged from quantum fluctuations in a field beyond time, you are left facing the same mystery. How do you get something from nothing? Why is there something rather than nothing at all? These are questions not just for the devout or the skeptic, but for all who have ever looked into the night and wondered. They are not only about the origin of the universe, they are about the origin of meaning. If our universe had a beginning, what triggered it? This question has inspired generations of scientists to explore possibilities that stretch the limits of logic, mathematics, and imagination. One idea suggests that the universe may be part of a never-ending cycle, a cosmic heartbeat of expansion and contraction. In this view, the Big Bang was not a singular beginning, but just one beat in an eternal rhythm. The universe expands, cools, collapses, and is born again. No true start, no final end, merely a dance that spans eons, echoing through time without origin. Another possibility is even more astonishing. What if our universe was created not in isolation, but in a collision, two vast universes, or higher dimensional membranes, crashing into one another in a space beyond our own? This idea, known as brain cosmology, proposes that our three-dimensional reality floats like a sheet in a higher dimensional space. A collision with another brain could have unleashed the energy that formed everything we see today. In this scenario, universes may not be rare at all. They may be colliding, emerging, and vanishing constantly in an unseen multiverse. But perhaps the most radical theory is also the simplest, and the most unsettling. Perhaps the universe came from nothing, not a vacuum, not empty space, but truly nothing. No time, no space, no fields, no laws, just non-existence. And yet, from this absolute absence, existence emerged. Something from nothing. How could this be? How can there be a cause without time? How can there be creation without a creator? This idea defies intuition, yet it continues to gain attention, not because it is comfortable, but because mathematics and physics suggest it might be possible. Quantum mechanics tells us that particles can emerge spontaneously from the vacuum, so long as they vanish quickly enough to conserve energy. Space itself may not be truly empty, but rather seething with activity at the tiniest scales. Could the universe be a larger version of this, a single cosmic fluctuation that happened not in space, but in nothing? Some physicists believe that if the total energy of the universe adds up to zero, positive energy in matter, balanced by negative energy in gravity, then perhaps its existence does not violate any law at all. These hypotheses do not end the mystery. They deepen it. If the universe was born from a previous one, what began that chain? If it came from another dimension, what lies beyond it? And if it came from nothing, what is that nothing made of? Is it even meaningful to speak of where or when before space and time? These are not questions with easy answers, but they point us toward the limits of knowledge, and perhaps toward a deeper truth. No matter how we frame it, we are left with a haunting realization. Everything we know and love may have come from something we cannot yet imagine. For centuries, the universe was a machine, predictable, precise, governed by the clockwork laws of Isaac Newton. Planets followed elliptical paths. Objects fell with measurable force. Time marched forward at a steady pace. Everything could be calculated, given enough information. It was a world where certainty reigned, and mystery faded under the light of reason. In this classical view, the cosmos was not chaotic. It was ordered, mechanical, and knowable. And for a time, it seemed that physics had nearly finished its task. But the cracks began to appear. As scientists peered deeper into the atom and observed light from distant stars, inconsistencies emerged. Some things did not fit. Light, for example, behaved strangely, sometimes as a wave, sometimes as a particle. Black-body radiation, the glow from heated objects, defied explanation. The orbit of Mercury deviated slightly from Newtonian predictions. These were not small glitches. They were clues that the universe was far stranger than classical physics had imagined. In the early years of the 20th century, Albert Einstein shattered the illusion of time itself. His theory of special relativity revealed that time and space were not fixed backdrops, but flexible dimensions that changed depending on speed and gravity. The faster one moved, the slower time would pass. Clocks could tick at different rates. Simultaneity, once a bedrock of logic, was no longer absolute. Einstein had not merely revised Newton's laws, he had redefined the very fabric of reality. Yet, even Einstein's revolution could not explain the deepest mysteries of the subatomic world. When scientists began probing the atom, they encountered a realm that defied all intuition. Electrons did not follow neat paths around nuclei, like planets around stars. Instead, they flickered in and out of certainty. Their position could not be pinned down without disturbing their motion. Measurements gave probabilities, not certainties. It was a world of shadows, not sharp outlines. Classical physics had no language to describe this. The response came not from a single theory, but from an entirely new framework: quantum mechanics. It began quietly, with Max Planck's proposal that energy was not continuous, but came in tiny, indivisible packets called quanta. Then came Einstein's insight that light itself was made of particles, photons. The floodgates opened. Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and many others laid the foundation for a new physics. It was unlike anything before it. In this new world, particles were also waves, and waves were also particles. Nothing behaved in isolation. Observation itself altered reality. The rise of quantum mechanics marked a turning point in human understanding. The universe was no longer a machine made of solid parts. It was a field of probabilities, of shifting patterns and potentialities. It was no longer about where something was, but where it might be. Cause and effect blurred. Certainty dissolved. The comforting determinism of Newton had given way to a strange new world, one that felt more like poetry than clockwork. But as unsettling as it was, this new vision of reality would soon reshape our understanding of the atom, the star, and the entire cosmos. In the summer of 1925, a young physicist named Werner Heisenberg found himself overwhelmed. For months, he had struggled to make sense of the atom, of electrons that refused to behave, of theories that collapsed under their own complexity. His mind was exhausted, his hay fever relentless. Seeking clarity, he left the academic halls of Göttingen and retreated to the wind-battered island of Heligoland, a speck of rock in the North Sea, where sea air replaced pollen and silence replaced pressure. It was here, in isolation, that he would uncover one of the greatest revolutions in the history of physics. Heisenberg had been wrestling with a fundamental problem: how to describe what electrons were doing inside atoms. Classical models imagined them like miniature planets orbiting a nucleus, but this picture failed. Electrons did not behave like tiny balls. Their motion was not smooth, not predictable. The existing mathematics could not keep up. Heisenberg began to ask a new question. What if the problem was not the particles, but our insistence on knowing too much? What if we abandoned the idea of exact paths altogether and instead focused only on what could be observed? This shift in perspective was radical. Instead of trying to map the invisible motion of electrons, Heisenberg turned his attention to the things we could actually measure, like the frequencies of light emitted when electrons jumped between energy levels. He stripped away the unobservable, the imagined orbits, the classical baggage. Then, late one evening on Heligoland, the mathematics began to take shape. What emerged was strange, alien even. His new equations did not use traditional variables. They used arrays of numbers, matrices. At the time, this was a mathematical novelty in physics. Heisenberg did not sleep that night. As the sun rose over the sea, he walked the cliffs of the island, stunned by what he had found. The equations worked. They matched experimental data. They did not describe where an electron was, only where it might be. They said nothing about the path between states, only the probabilities of transitions. In a single night, the vision of the atom had shifted. Matter was no longer solid. Reality was no longer exact. At its core was uncertainty. mathematical, measurable, and unavoidable. What Heisenberg had discovered would soon be known as the uncertainty principle. It stated that the more precisely we know a particle's position, the less precisely we can know its velocity, and vice versa. This was not a limitation of instruments or technology. It was a law of nature itself. There was a built-in fuzziness to the universe. At quantum scales, the very act of measurement disturbs the system. The electron does not sit quietly, waiting to be found. It exists in a cloud of possibility until we look, and then collapses into one of many outcomes. Together with Schrödinger's wave equation, Heisenberg's new matrix mechanics redefined the foundations of physics. It was no longer about predicting certainty, but understanding likelihood. The electron became a wave of probability, and the atom a blur of potentials. The mathematics was difficult, the implications profound. But this quantum framework would soon explain the structure of matter, the chemistry of life, and the light of stars. And it all began on a quiet island, where a young scientist, plagued by hay fever, cleared his mind and saw the universe not as it seemed, but as it truly was. We often think of a vacuum as the ultimate emptiness, a place without air, without matter, without anything at all. It is the closest thing we can imagine to nothingness. In space, between the stars and galaxies, vast regions seem to lie in utter silence and stillness. No atoms drift there, no photons scatter. To the naked eye, it appears completely empty. But this image is an illusion. At the quantum level, even the vacuum is alive. It seethes with activity, hidden, restless, and constant. The emptiest space is not truly empty. In the world of quantum mechanics, a vacuum is not a passive void. It is a stage where invisible players are always moving. Particles and antiparticles appear and disappear in brief flashes, too quick to be directly seen, yet real enough to affect the universe. These are known as virtual particles, and they exist because the laws of quantum physics allow tiny violations of energy so long as they do not last very long. For the briefest of moments, the vacuum borrows energy to create a particle pair and then repays the loan by making them vanish. These fluctuations may seem like a mathematical trick, but they have very real consequences. They create a subtle background energy that fills all of space, what physicists call the quantum vacuum energy. It is this energy that allows particles to tunnel through barriers. It affects the behavior of atoms and the structure of matter. It even contributes to the force known as the Casimir effect, where two metal plates placed close together in a vacuum feel a mysterious pressure pushing them inward, caused by the absence of certain virtual particles between them. The most astonishing implication of this is philosophical. If even the vacuum is never truly at rest, if even nothing cannot be still, then perhaps absolute nothingness is physically impossible. Perhaps there is no such thing as a complete void. Everywhere we look, even in the darkest corners of space, there is energy, there is motion, there is potential. What we once called nothing now appears to be the foundation of everything. The very fabric of reality is stitched from uncertainty, possibility, and invisible waves that ripple through the vacuum. This quantum vacuum may even help explain the origin of the universe itself. If space can never be truly empty, and if energy can spontaneously emerge, then perhaps the seeds of everything we know were planted within this restless sea. A universe from nothing may not be magic. It may be physics. And as strange as it seems, this vision of a vibrating, energetic void is not a poetic metaphor. It is the world described by our best theories, confirmed in our most precise experiments. In the end, the vacuum, the so-called nothing, turns out to be one of the most extraordinary somethings in existence. For most of human history, the sun was a mystery, a divine presence, a chariot of fire, a glowing orb in the heavens. But even as science began to unravel the laws of nature, one question lingered. What powers the sun? In the 19th century, Lord Kelvin, one of the great scientific minds of his time, believed the answer lay in gravitational compression. As the sun's immense mass pressed inward, it would heat up, glowing like an eternal forge. But there was a problem. By his calculations, the sun could only burn for a few tens of millions of years, far too short for the long story of Earth and life. This contradiction troubled scientists. Geologists saw evidence of an Earth hundreds of millions of years old. Biologists needed even more time for evolution to unfold. Clearly, Kelvin's model was incomplete. The missing answer lay deeper, inside the atom itself. In the early 20th century, physicists discovered that at the heart of every atom was a tiny, dense nucleus. Protons and neutrons bound together by an immensely powerful but short-range force. This strong nuclear force could release extraordinary amounts of energy if it could somehow be unlocked. The process that unlocks this energy is nuclear fusion, the merging of two lighter nuclei, like hydrogen, into a heavier one, like helium. But fusion comes with a paradox. The positively charged protons in hydrogen repel each other, like magnets turned the wrong way. To overcome this electrostatic barrier, the nuclei must be pushed extremely close together. Even in the sun's core, where temperatures reach over 10 million kelvins, the collisions are not quite forceful enough. Classical physics alone says fusion should not happen, and yet the sun shines. The key to this puzzle came from an unlikely source: quantum mechanics. In the 1920s, physicist George Gamow proposed that particles at the quantum scale do not behave like billiard balls. They exist in a blur of possibilities. Even if two nuclei do not have enough energy to climb over the barrier separating them, they might simply appear on the other side. This phenomenon is called quantum tunneling. It allows protons to bypass the rules of classical motion, briefly violating expectations in a way that makes fusion possible. Without quantum tunneling, the stars would be dark, the sun would not shine, the night sky would be empty. But thanks to the strange rules of the quantum world, Light and warmth flood the solar system. Every sunrise, every shadow cast, every green leaf photosynthesizing. These are the echoes of tunneling particles, slipping through invisible walls. It is a quiet miracle of physics, one that bridges the tiniest scales of the atom with the grandest scales of the cosmos. In this way, quantum mechanics does not just describe the universe, it illuminates it. In the beginning, the universe was simple: hydrogen, helium, a touch of lithium. These were the first elements, born in the fires of the Big Bang, and for a long time, that was all the cosmos had. But the beauty of stars is that they are not just sources of light, they are also factories. Inside their blazing cores, atomic nuclei are pressed together under unimaginable pressure. Through a delicate sequence of nuclear reactions, hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen. It is a slow alchemy, powered by fusion and guided by quantum rules. At each stage, the strong nuclear force binds particles together, overcoming the repulsive push of positive charges. But this force only acts across tiny distances. Nuclei must be forced into nearly direct contact before they fuse. In smaller stars, like our Sun, fusion stops at helium. But in massive stars, gravity squeezes their cores ever tighter, pushing atoms together until even heavier elements form: neon, magnesium, silicon, sulfur, and eventually iron. Iron marks a threshold. It cannot release energy through fusion. It is the end of the line. When iron builds up in the heart of a massive star, the balance is broken. The outward pressure from fusion fades. Gravity wins. The star collapses inward with incredible violence. In less than a second, matter falls toward the core at a significant fraction of the speed of light. And then, a rebound. The core stiffens. The infalling material crashes into it and ricochets outward. This is a supernova, the most powerful explosion in the universe. It tears the star apart. And in this final violent act, something extraordinary happens. The temperatures and densities in a supernova are so extreme that ordinary physics breaks down. Quantum effects take over completely. Particles that rarely interact suddenly matter. Among them is the neutrino, a ghostly particle with almost no mass, no charge, and no allegiance to the familiar forces of electromagnetism or the strong nuclear force. Normally, neutrinos pass through planets as if they were not there. But in the core of a collapsing star, they are so numerous, so dense, that they slam into matter and help drive the explosion outward. They unlock the energy needed to scatter stardust across the galaxy. And in those final chaotic moments, new elements are forged: gold, uranium, platinum. These are not made slowly, like carbon or oxygen. They are made in an instant, in the briefest heartbeat of the dying star. Nuclei capture neutrons faster than they can decay. This rapid-fire fusion, guided by quantum probabilities, fills the periodic table. Every atom of calcium in your bones, every atom of iron in your blood, was built in a star and released in a death cry. You are, quite literally, made of star stuff, born in quantum fire and scattered by cosmic winds. So, the universe is not simply shaped by quantum mechanics, it is composed of it. From the light in your eyes to the gold on your ring, from the breath in your lungs to the memories in your brain, none of it would exist without the delicate, probabilistic dance of particles and forces. Fusion, collapse, rebirth. Quantum mechanics is not just the science of the small. It is the architect of the stars, the engineer of the elements, and the silent scriptwriter of everything that ever was or ever will be. In quantum mechanics, everything begins with a wave function. It is a mathematical object that describes all the possible states a system can occupy, not just where a particle is, but where it might be and what it might become. For small things like electrons and photons, this makes sense. But what if we dared to scale it up? What if, instead of a single particle, we applied the idea of a wave function to everything, to every atom, every star, every galaxy? Could the entire universe itself be described as one enormous wave function? In the 1950s, a young physicist named Hugh Everett proposed a bold idea. If the universe is governed by quantum mechanics, then there is no single future, only many possible futures, each one encoded in the universal wave function. Rather than collapsing into one outcome when measured, the universe simply branches. Every possibility becomes real, in some alternate version of reality. This is the many worlds interpretation, where countless versions of you, of me, of everything, unfold side by side, silent, unreachable, but mathematically inevitable. It is a vision of reality that is both thrilling and unsettling. In this view, the universe is not a single story, but a library of every story that could ever be told. The laws of quantum mechanics do not merely shape atoms, they shape destinies. And if this interpretation is true, then the wave function of the universe is not just a tool. It is the ultimate description of reality. A quantum cosmos, unfolding not by certainty, but by possibility. A place where even now, in some branch of the multiverse, the future is taking a different turn. When we speak of the beginning of the universe, we often picture an explosion, an event that happened at a moment in time, at a specific point in space. But what if that image is wrong? In the early 1980s, physicists Stephen Hawking and James Hartle proposed a radical idea. Perhaps the universe did not begin in time, but with time. In their model, time itself is not an infinite line stretching into the past. Instead, it emerges gradually from a strange and timeless realm shaped by quantum rules. This idea arose from a fundamental problem in cosmology, the singularity. According to Einstein's general theory of relativity, if we rewind the expansion of the universe far enough, we reach a point of infinite density and temperature, a singularity where the known laws of physics break down. But infinities are the warning signs of broken mathematics. They signal that our equations have reached their limits. Hawking and Hartley believed that if we applied quantum mechanics to the birth of the universe, we might be able to remove the singularity entirely. To do this, they used a bold mathematical tool called imaginary time. In this framework, time behaves more like a spatial dimension. There is no sharp boundary, no edge where time suddenly begins. Instead, the early universe is smooth and curved, like the surface of a sphere. You can travel to the South Pole, but there is no point south of it. Similarly, in the Hartle-Hawking model, there is no moment before the Big Bang, because time itself does not extend past that boundary. It is not that there was nothing, it is that there was no when for anything to happen. This view is profoundly counterintuitive. We are so accustomed to time being a backdrop, a river that flows in one direction, always ticking forward from a beginning. But in this quantum cosmology, time is not fundamental. It is emergent. It crystallizes out of a more primitive, timeless state governed by quantum fluctuations and probabilistic laws. In this early state, the distinctions between space and time blur. There is no past, no future, only potential, a haze of possibilities out of which the classical universe slowly emerges. In removing the singularity, the Hartle-Hawking model does not just smooth out the mathematics, it reshapes our understanding of origin itself. It implies that the universe has no absolute beginning, no sharp edge. It is finite, but without a boundary. It simply is. There was no before, because time is not something that existed prior to the universe. It is something that came with it, like light, or gravity, or matter. This is not just a scientific proposal. It is a philosophical shift. It forces us to rethink what it means for something to begin. Of course, not everyone agrees with this model. Cosmology is filled with competing theories, and the ultimate nature of time remains one of its deepest mysteries. But the Hartle-Hawking proposal opened a door, a way to think about the universe without falling into paradox. It blends the quantum with the cosmic, the abstract with the profound. And though we may never fully grasp what came before, this vision suggests something beautiful, that the universe did not erupt from a singular point, but gently unfolded from a timeless sea, where being and becoming are the same. By the late 20th century, cosmologists had gathered strong evidence for a universe that began in a hot, dense state and has been expanding ever since. But this simple picture left behind puzzles. Why is the universe so smooth on large scales, with distant regions showing almost identical properties, despite being too far apart to have ever communicated? And why is space so geometrically flat, as if it were balanced on a cosmic knife's edge? These questions pointed to a missing piece in the story of creation, a moment that came just after the Big Bang. In 1980, physicist Alan Guth proposed a bold solution: cosmic inflation. According to this theory, in the first fraction of a second after the universe was born, space itself expanded at an unimaginable rate. Not just fast, exponentially fast. Regions smaller than an atom suddenly ballooned to macroscopic size. In a cosmic blink, a tiny quantum fluctuation became the seed for all the structure we see in the universe today. Inflation did not just smooth out the cosmos, it amplified the tiniest imperfections into the scaffolding of galaxies. Inflation explains the large-scale uniformity of the universe by making distant regions once close enough to interact. It also explains why space appears flat, because a small, curved patch inflated so rapidly that it now looks flat, just as the surface of the Earth appears flat to someone standing in a field. But perhaps the most profound implication of inflation is what it did to quantum fluctuations. Tiny, random variations in energy, normally confined to the microscopic world, were stretched across the sky and frozen into the very fabric of space. These quantum fluctuations, expanded to cosmic proportions, became the seeds of galaxies, stars, and planets. Where there was a slightly higher density, gravity pulled in more matter. Over billions of years, these small differences grew into the vast structures we see in the cosmos, clusters of galaxies, cosmic filaments, and dark voids. The universe we know, with its brilliant complexity and order, may have emerged from random quantum jitters magnified by inflation. It is a breathtaking idea that the stars themselves are echoes of uncertainty. Inflation also offered an elegant answer to another mystery: why we do not see certain predicted relics from high-energy physics, like magnetic monopoles. If they existed in the early universe, inflation would have diluted them to such a degree that they would be essentially unobservable today. In this way, Guth's theory solved multiple problems at once. It connected the physics of the incredibly small, the quantum field, with the vastness of the cosmos, suggesting that what happens in the silence of subatomic space can shape the architecture of entire galaxies. Today, inflation remains a leading theory in cosmology, supported by precise measurements of the cosmic microwave background, the ancient light still echoing from the early universe. Yet, questions remain. What triggered inflation? What ended it? And what was the nature of the quantum field that drove it? Whatever the answers may be, one truth stands clear. The early universe was not just governed by quantum mechanics, it was sculpted by it. From a formless quantum haze, a universe was born. And within that unfolding fabric, every star, every planet, and every one of us found our place. In the early 1970s, a young physicist named Edward Tryon sat in a lecture hall, listening to a presentation on the mysteries of the cosmos. At some point during the talk, he raised his hand and posed a strange, almost playful question. Could the universe be a quantum fluctuation? There was a quiet laugh in the room, as if he had made a joke. But Tryon was not joking. He had been thinking deeply about the nature of nothing, about the vacuum, and how quantum physics allows temporary violations of energy conservation, so long as they do not last very long. In quantum mechanics, The vacuum is not truly empty. It is a restless medium, filled with fleeting pairs of particles that emerge and disappear in the blink of an eye. Tryon wondered, if these fluctuations can briefly bring particles into existence, could one of them, under just the right conditions, expand and stabilize? Could the entire universe itself be such a fluctuation, emerging from a quantum vacuum, not as a permanent thing at first, but as a brief, spontaneous event that somehow lasted forever? It was a radical thought, but it pointed to something remarkable. Tryon realized that if the total energy of the universe were zero, this idea might not violate any law of physics. Positive energy exists in the form of matter and motion, but gravity, always attractive, carries negative energy. If these two energies perfectly cancel each other out, the net energy of the universe could be nothing at all. A zero-energy universe, born from the quantum vacuum, might be allowed to exist indefinitely. It would not cost anything to create, because in the strictest sense, it would require no energy at all. Of course, this idea leads to an even deeper question. Where did the vacuum itself come from? What fluctuated if nothing existed? Tryon admitted that such questions lay beyond current physics, yet his insight marked a profound shift. It suggested that the universe might not need a cause in the traditional sense, that it could be the product of the same uncertainty and fluctuation that governs the quantum world. In this view, the universe is not a divine creation or a metaphysical necessity. It is a moment of possibility, an echo of nothing made real. In the grand time scale of the cosmos, stars are fleeting. Some burn bright and fast, living only for millions of years. Others, like our sun, persist for billions. But even the longest-lived stars cannot shine forever. Eventually, they exhaust their nuclear fuel. Without the heat generated by fusion, gravity begins to dominate. The star collapses inward. What remains depends on its mass. Smaller stars become white dwarfs, hot, dense embers that slowly cool. Larger ones may become neutron stars or collapse further into black holes. These are the corpses of stars scattered across time. But even after fusion has ended and starlight fades, quantum mechanics continues to play a role. In white dwarfs and neutron stars, particles are squeezed into impossibly tight spaces. Yet something holds them up: the uncertainty principle. The more we confine a particle, the less we can know about its momentum. This gives rise to a pressure, not from heat, but from quantum uncertainty. It is called degeneracy pressure, and it is the only thing preventing these dead stars from collapsing completely. Even in the cold dark, quantum rules do not sleep. Still, time marches on. Trillions of years pass. Even the dimmest red dwarfs, stars that burn their fuel with utmost efficiency, eventually go dark. The universe enters an age of remnants. White dwarfs fade to black. Brown dwarfs, never bright enough to ignite, cool into cold, invisible husks. Black holes remain, massive and silent. This is the twilight of the cosmos, a time when no new stars are born, when the galaxies have dimmed, and matter itself begins to question its permanence. But even this stillness is not the end. Physicists have long wondered whether protons, the building blocks of atomic nuclei, are truly stable. Some theories suggest they are not. According to these ideas, a proton might one day decay, turning into lighter particles through processes governed by forces we have yet to fully understand. If true, then over unimaginable spans of time, perhaps 10,000 trillion years, every atom in the universe would eventually fall apart. Matter, as we know it, would dissolve into radiation and dust. A slow and silent disintegration. This would mark the final unraveling. No more stars, no more planets. Just a thin haze of particles drifting through a cold and empty space. The universe would have no structure, no complexity, no warmth. It would be quiet, but not peaceful. Yet even this decay, like everything before it, would be driven by quantum principles. The same laws that gave birth to the stars now oversee their final breath. The universe, born from quantum uncertainty, fades according to the same rules. The story bends inward, toward stillness, toward nothing. And yet, there is something hauntingly beautiful in this vision, that the vast architecture of galaxies, the light of stars, the very chemistry of life, all emerged from a flicker of uncertainty, and that, in the end, all of it returns to that same silence. The death of stars is not merely the end of heat and light, it is a passage, a return. Quantum physics does not just shape the birth of the cosmos, it shapes its farewell. In the farthest future imaginable, when even the protons have decayed, the universe will whisper its final truth. From uncertainty we came, and to uncertainty we shall return. For a long time, black holes were thought to be eternal. These strange objects, where gravity becomes so strong that not even light can escape, seemed like the final, inescapable prisons of matter. Once something crossed the event horizon, it was gone forever. No signal could return. No information could be retrieved. Black holes were not just mysterious, they were absolute. They marked the end of time for anything that fell inside. And for decades, physicists believed that they would endure forever, growing darker and more massive with every passing age. But then came a breakthrough from Stephen Hawking. In the early 1970s, he asked a simple but daring question. What happens at the edge of a black hole if we apply the laws of quantum mechanics? The answer changed everything. According to quantum field theory, even empty space is not truly empty. It seethes with fluctuations, virtual particles that blink in and out of existence. Near the event horizon, these fluctuations become lopsided. One particle may fall in, while the other escapes. To an outside observer, it appears as though the black hole is radiating. This phenomenon, now known as Hawking radiation, means that black holes are not entirely black. They emit tiny amounts of heat, and because nothing escapes a black hole without cost, this radiation carries away mass. Over immense periods of time, a black hole slowly loses energy, shrinks, and eventually evaporates. The darker it becomes, the faster it fades. What once seemed indestructible now has a lifespan. Quantum mechanics, silent and subtle, chips away at the edges of darkness, turning the most feared object in the universe into a fading ember. The discovery of Hawking radiation is more than just a correction to black hole physics. It is a glimpse into a deeper truth, a bridge between gravity and quantum theory. It shows that even at the edge of the unknown, the rules of the quantum world still apply. That space is never still. That energy is never truly lost. And that no darkness is absolute. In the end, quantum mechanics does not just light the stars. It pierces even the deepest shadows, reminding us that the universe, no matter how vast or cold, is never beyond the reach of subtle, flickering light. For over a century, physics has been guided by two towering frameworks. On one side stands general relativity, Einstein's theory of gravity, which describes the cosmos at the grandest scales, stars, galaxies, and the shape of space-time itself. On the other side is quantum mechanics, which governs the tiniest particles, revealing a world of uncertainty and probabilities. Both theories work brilliantly in their own domains, but they do not speak the same language. At their intersection, black holes, the Big Bang, they clash. And there, our understanding begins to break down. Physicists have long dreamed of uniting these two pillars into a single, elegant theory, a theory of everything. It would explain gravity, quantum forces, and the fundamental particles in one mathematical structure. Einstein spent the final decades of his life chasing this vision, but the pieces never fit. Others have tried since. String theory imagines that particles are not points, but tiny vibrating loops. Loop quantum gravity sees space-time itself as woven from discrete threads. These ideas are bold and beautiful, but none have yet passed the ultimate test: experimental proof. Still, the dream persists. The hope of one equation to describe it all, matter, energy, space, and time, is too powerful to ignore. Perhaps the universe is not built from separate parts, but from one deep, unified reality we have not yet fully grasped. Perhaps one day we will find the key that connects quantum foam to the curvature of space-time. Until then, we remain explorers in a vast mathematical landscape, chasing echoes of a truth just beyond our reach, a single theory that would reveal the entire cosmos in one breath. Across this journey, we have traced the arc of existence, from a whisper in the quantum vacuum to the birth of galaxies, from the blazing heart of stars to the cold silence of eternity. We have seen that nothing is never truly nothing, that emptiness trembles with possibility, that the universe, with all its complexity and order, may have emerged not from design or necessity, but from fluctuation, a ripple in the stillness, a chance event that gave rise to space, time, matter, and eventually to us. It is humbling to think that the atoms in our bodies were forged in the hearts of dying stars, scattered across the cosmos by forces indifferent to meaning. And yet, here we are, conscious, questioning, aware. If the universe is a wave function, then we are part of that wave, a crest momentarily rising in the sea of probabilities. Perhaps we are not the center of creation, but a rare configuration of particles where the universe briefly looks inward and asks itself, "What am I?" Science tells us how the universe works, but it cannot always tell us why it should exist at all. If everything emerged from nothing, what does that say about purpose? About meaning? Are we a story written in mathematics, or a miracle suspended in chance? If the cosmos is a quantum dream, endlessly branching and unfolding, then perhaps our lives are no less real for being fleeting. Perhaps we matter not because we last, but because we think, feel, and wonder, because we ask questions like this one. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.